good morning, everybody, and happy Independence Day to all. So I welcome you to the day 3 of the student seminar 2021. The chair for today's session is Amlan Subramanian. He is currently a PhD student at IIT Madras. So welcome, Amlan, and over to you now.
Thank you, Karan. I'm so thankful for the opportunity to chair this session. Today's first session is by Amlan Sinha, who is currently pursuing integrated MSc in Mathematics and Computing at BIT Meshra. He's an alumni of MTTS programs from mini MTTS to MTTS level O, level 1, and also he has been a mentor for the foundational courses. Today he will be talking about the equivalence of sequential definition and epsilon delta definition of continuity of functions, with discussing some of the continuity of some functions. So I would like over to you, Amlan. Next 20 minutes is for you. We'll give you a kind reminder at 15 minutes. That is, when you have last 5 minutes, I'll give you a kind reminder. Over to you.
Thank you, Amlan sir. My topic for today's VSSP is equivalence of the sequential definition of and the epsilon delta definition of continuity of real functions. So let us take it slowly. At first, let's see what these two definitions are. So the definition 1, as I will be denoting it as definition 1, the epsilon delta definition. So let J be a subset of R and F is defined from J to R with function, and A is a point in J. We say that the function F is continuous at A if for a given epsilon positive, there exists a delta positive such that if X is in J and mod X minus A is less than delta, then mod of Fx minus Fa is less than epsilon. Yeah, let us see what this really means. It means that suppose I have been given an epsilon positive and I have been given a point A. So if I take the image f of A and around this f of A, if I take the interval f of A minus epsilon to f of A plus epsilon, then there will exist a delta such that in the interval A minus delta to A plus delta, if I take a point X and take its image, then the image fx will lie in this interval fa minus epsilon to fa plus epsilon. So this is the first definition. And the second definition, which is the sequential criteria, it says that taking the same considerations, we say that f is continuous at A if for every sequence in J, say xn, which converges to A, will have f of xn converging to f of A. So these are the two definitions. And whenever we talk about function, we the two most natural functions which come to our mind is first of all, it's a constant function, and the second one is the identity function. So let us see how we can discuss the continuity of these two functions in both the ways. So my first we discussed is the constant function. It is different that if f is a constant function, then we define fx as some c, constant c. So let us discuss at any point A. An epsilon positive which is given. So if I take any x in the interval A minus delta to A plus delta, our motive is to find that this delta, right? And we need to estimate f of x minus f of a. So at first, let estimate this modulus of f of x minus f of a. But we know that this is nothing but modulus of c minus c, since f of x is a constant function. So this value is 0, and this is less than epsilon. But the fact that this is less than epsilon, whatever delta we choose, it means that for any given epsilon positive, we will have a delta. Say delta is equals to 1. So we can say that this function f, the constant function, is continuous at point A in J. But since A is arbitrary, so we say that the constant function is continuous everywhere. Now, by definition 2, let us take a sequence xn in J, which converges to A. So, what we need to see that how f of xn, the sequence f of xn, behaves, right? So we know that for every x, fx is c. So for each xn, f of xn will be c. Hence, this sequence f of xn, it's nothing but a constant sequence with limit c. So we can say that f of xn converges to c, but c is nothing but f of a. Hence, we can say that f of xn converges to f of a. So the constant function is continuous at a, and again, since a is arbitrary, so we can say that constant function is continuous everywhere. Now, the second most natural example which comes to our mind is the identity function. Say we know that how it is defined. We define the constant function on R as f of x is equals to x. So x maps to x. Now let us say that we take any point A in J or in R, right? So let us see what we can say about the continuity at A by definition 1. So given there is a positive epsilon, and we need to find this delta, right? So at first we see how we can estimate this f of modulus of f of x minus f of a. Like we know that f of x is x and f of a is a. So modulus of f of x minus f of a is modulus of x minus a. So if I choose my delta to be equal to epsilon, then we are done. Clearly, this equality epsilon is equals to delta. This satisfies the criteria. Hence, by definition 1, we can say that the identity function is continuous everywhere. Now let us see what we can conclude by this definition 2. So let us take a sequence xn in J such that xn converges to A. Clearly, we know that for each n, f of xn will be xn, right? And so the sequence of f of xn is nothing but the sequence xn itself. Hence, we can say that f of xn converges to A, which is nothing but f of a. So the identity function is continuous at A. Since again A is arbitrary, so we can say that it is continuous everywhere. But till now, these two examples, we have seen that the function is continuous everywhere. We may came across some functions which are not continuous, and more interestingly, we can come across some functions which are not continuous anywhere. So let us see how we can deal with that. Yeah. So yeah, this is a point which we need to see that when a function is not continuous at a point A in J, it means that even if the sequence, I'm just explaining it in terms of the sequential criteria, which will be very we can visualize it, that if suppose we have that this sequence xn which converges to A, but it may happen that the sequence f of xn, it does not converge to f of A. Even it may happen that the sequence may not converge at all, right? So let us look at our third example, and this is an example. This function's name is Dirichlet function. So we define it from R to R, and we say that f of x is 1 if x is a rational number and it's 0 otherwise. So we claim that this function is not continuous at any point in R. So I am doing it through one way, and I will just give hints of the other. So let's discuss it through the sequential criterion. So suppose let us take any arbitrary point A in R. So we know by density of rationals and irrationals that there exist sequences of rationals xn and sequences of irrationals yn, such that xn converges to A and yn also converges to A. So for we know that since these sequences of xn, they are of rationals, right? So for each n, we'll have the mapping f of xn as 1. And similarly, since yns are irrationals, So f of yn for each n is 0. So we have chosen A in R. If the chosen point A is rational, then we see that this xn converges to A, but sorry, yn converges to A. Yn, that is the sequence of irrationals, converges to A, but f of yn, it converges to 0. But we know that f of A is 1, and that is not equal to 0. So we can say that if A is any rational point, then Dirichlet's function is not continuous at A. Now let us see when A is irrational, what happens. Again, we see that we have a sequence of rational ones. So for each n, f of xn is 1. So it is a constant function, sorry, constant sequence. So f of xn converges to 1. But since A is irrational, so f of A is 0. Hence, they are not same. So what we can say that if A is any irrational point, then Dirichlet's function is not continuous at that A. Hence, Dirichlet function is continuous nowhere in R. So yeah, this I explained by the sequential criterion, and just take the hints I would expect from the viewers that take any epsilon which is 1 or less than 1, and estimate f of x minus f of A. Take in both the cases when A is rational and irrational, and you will see something which hinders our definition of the epsilon delta, so they will not be continuous. Yeah. Next, we come across this equivalence thing, and as we have just observed that it depends upon the function and the complexity of the function, that whether at a point we want to use the definition 1 to show the continuity or definition 2. But what I want to claim is that these two definitions are equivalent. So let us see how definition 2 implies definition 1. That is, the sequential criterion implies the epsilon delta definition. So let f be not continuous at A according to the definition 1. So clearly, we are taking the negation of that statement in definition 1, that there will exist some epsilon positive, such that no delta as required exists. What does this mean, that no delta as required exists? That is, for all delta positive, there exists an x in j in the section A minus delta to A plus delta, such that this estimate mod of f of x minus f of A is greater than equal to epsilon, right? So we have assumed that it is not continuous. Let us see what we can say. So I will construct here a sequence. Let us look at this sequence xn. We know that whenever we talk about estimates, the most natural estimate which comes to our mind is 1 upon n. So let us take our delta to be 1 upon n. Then from each these intervals, a minus 1 upon n to a plus 1 upon n, we can have this xn and form a sequence, right? But and also we know that for each of these xn, f of xn minus f of a is greater than equal to epsilon. What we know that by sandwich lemma, this xn converges to A. So by definition 2, that is a sequential criterion, we know that f of xn will converge to f of A. But again, from this we can conclude that the modulus of f of xn minus f of A converges to 0. So what we have seen that this is true, that is modulus of f of xn minus f of A is greater than equal to epsilon, and also we see that modulus of f of xn minus f of A is, it converges to 0. This cannot happen since for all n this is true, right? Hence, what we have assumed, there is a contradiction in that, and hence we say that f is continuous at A by definition 1, 2. That is, by epsilon delta definition 2, we can say that f is continuous at A. Now let us see the other way, that how definition 1 implies definition 2. That is, we need to see that if we are given a sequence in J such that xn converges to A, we need to show that f of xn converges to f of A. But what we have is that for any epsilon positive, we can have a delta positive, that is, there exists a delta positive such that whenever I take an x such that modulus of x minus a is less than delta, we'll have modulus of fx minus fa less than epsilon. So let us so for this epsilon positive, we will have some delta positive, right? And we know that xn converges to a. So for this particular delta positive, we will have a natural number capital N, so that for all n greater than equal to n, modulus of xn minus a is less than delta, right? This means that for all n greater than equal to capital N, xn is an element in the interval e minus delta to a plus delta, and we have assumed that the function is continuous by definition 1 at a. So we can say that f of xn will lie in this interval, right? So what we can say that this sequence f of xn, it converges to f of a. Hence, we can conclude that the function f is continuous at a by definition 2 also, that is by sequential criterion also. Thus, we have shown the equivalence of both the definitions. And I guess now I have time, so I will just discuss this
Amlan,
last function.
a kind
Yes.
reminder, you have your last 4 minutes.
Yeah, thank you. Yeah. So yeah, in the last 4 minutes, yeah, I will discuss this interesting function, and I will just give few hints. It's not a textbook, but it is not written in the textbook way. I'm giving few hints. So the function is Thomae function. It is defined from the open interval 0, 1 to r, and we define it as f of x is 0 whenever x is irrational, and f of x is 1 upon q whenever x is of the form p by q, such that p and q are natural number and p and q are coprimes. That is, their GCD is 1, right? So this function, we want to show that it is continuous at all irrational points, and it is not continuous at all rational points in 0, 1. So let's discuss it. Here I will use both the ways. For the rational one, I am using the sequential criterion. So let us take A be any rational point in 0, 1, right? So let us see that xn is a sequence of irrationals. It says that xn converges to A. Now we know that since this xn is a sequence of irrationals, each xn is irrational, we have this f of xn is equals to 0 for each n. Hence, this f of xn, it converges to 0, but 0, we know that a is rational, so f of a will not be 0, since it will be some 1 upon q. So f of xn does not converge to f of a. Hence, f is not continuous at any rational point. I would just give few hints to the viewers that we can also show this that it is not continuous at any rational point through epsilon delta approach. And I will just give that we will again observe that the density of irrationals helps us in that approach also. So that's the hint. Now let us move to the points of irrationals numbers. So let A be any irrational number, and let we epsilon positive be given. So I'm saying that by Archimedean property, there will exist some k, such that 1 upon k is less than epsilon. Why I have taken this k, I am explaining it right now. Yeah. So just look at this arrangement of the rational numbers, and you see I've used different colors. So let us see this 1 upon 1, then 1 upon 2 with denominator 2. Then we are seeing other rational numbers with denominator 3, that is 1 upon 3, 2 upon 3. Again, 3 upon 3 is 1, so it is already contained here. Right? Then 1 upon 4, 3 upon 4. We are not saying 2 upon 4, since 2 upon 4 is 1 upon 2, so it's here. So similarly, we will get 1 upon k and till k minus 1 upon k. And again, in this way, we can just write the rationals in this manner. So clearly, we can see that in 0, 1 interval, only a finite number of rationals points which are of the form p by q, such that this q is less than k. These are very finite number of rational points, and hence we can conclude that there will exist some delta, such that in this interval a minus delta to a plus delta, no rationals of the form p by q with q less than k. The hint is for this delta is that just take the minimum of modulus of a minus p by q. Okay, so that's for the viewers. So yes, so we have found this interval. So if I take any x in this interval, and if we want to estimate modulus of f of x minus f of a, so we know that this a is irrational. So we know that it is 0, and if again my x is irrational, so this estimate is equals to 0, and whenever my x is of the rational form, that is of the form p by q, where p and q are co-primes, p and q are co-primes and p and q are natural number, so the mapping will be of the form 1 by q, but this 1 by q is again less than equal to 1 by k, that is less than epsilon. Hence, for any epsilon positive, we have found a delta such that this estimate is less than epsilon. So we are done. And this proves the continuity of f at every irrational. So this was a Thomae function. And by this, I am ending up my presentation. Thank you. The references for this presentation, I would like to mention the book of Ajit sir and Eskumarasan sir. And also, I have referred to Real Analysis by S.K. Maka.
Thank you, Amlan. A nice presentation and a nice choices of examples that you put.